Okay, this short video is going to take a look at the Fourier Analysis Tool of Circuit Maker. So let's share my screen here with you and bring up Circuit Maker. And let me put myself up in the corner. So here's a circuit that shows a 1 kilohertz signal generator, and all there is a 1 k ohm resistor for the load. Now, if we had an oscilloscope, what we'd see is, the sine wave out of the signal generator. And I'm going to run this. And lo and behold, we do have an oscilloscope down here, but we also have this device up here. Now, to activate this device, I'm going to stop this. You go to Simulation, Analysis Setup. And what happens is you look at Transient Fourier, and it's probably a little bit mysterious how to set this up, and I'll kind of leave it there, I guess. We do a start time, stop time, step time, fundamental frequency, a number of harmonics, and we hit OK. And again, I've set this up to do what I want to do in this experiment, and it takes some studying to figure out how to set the thing up. So I'm not going to go in that too much deeper. Anytime I ask you to use this tool, I'll give you, a already made circuit with the settings already set. It's a little bit different from the Bodie plot, where I clicked on AC, and I have a start and stop frequency and number of test points. This is the default 1 hertz to 4 hertz, and 3 test points. That wouldn't show you very much. So anyway, a transient Fourier is where you set this up. So I'm going to exit this and go back again and run it. So the oscilloscope we don't care about too much. So I'm going to get rid of that guy, get rid of this scope, and take a look at this guy over here and blow it up. So what happens is you have this screen, and this is similar to what you would call a spectrum analyzer. And it starts at 0 hertz here. And this one, the screen is linear. Of course, we could change that if we want. 1.5, 3 kilohertz, 4.5 kilohertz, 6 kilohertz, 7.5 kilohertz, and 9 kilohertz. So the screen goes from 0 to 9 kilohertz, and that was set up by the settings that get up here in simulation. The scale over here goes up linearly, and we could change that to logarithmically if we wanted. And it turns out that so the y-axis is linear, and the x-axis, so the y-axis would be linear in its amplitude, or power, if you will. A spectrum analyzer will demonstrate power. And this guy here is frequency. So again, if I go back, let's stop it and run it again. And the oscilloscope's not coming up. I got to go to Window to grab the scope. And here we have the scope. If we take a look at an oscilloscope, and let's go hit automatic here. It's already automatic, I guess. We see the time display of the signal, how many cycles per second and so forth. And again, the center of the screen is 0, where the upper half is positive, the lower half is negative. So we call this the time domain, looking at a signal time domain, how it changes in time. Okay, so I'm going to get rid of this again. This we call the frequency domain. And you might recall what we had for a signal. It was a single signal coming out of the signal generator. So let's go back to take a look at that. Let's maybe make this smaller. And first off, we've got a little bit of a problem here that it says it's a 1 kilohertz signal, but maybe let's see what happens here. No, I already got a problem. I hate to have this not operate correctly. Let me go and change the frequency here. See, Circuit Maker has a lot of idiosyncrasies. I'm going to edit the signal generator. It says it's a 1 kilohertz signal, and let's make it 2 kilohertz. And hit OK. And then take and run it. And OK. So whatever was going on before, most likely I could have gone over here and probably hit the counterclockwise arrow, and I probably would have scored it away. But anyway, so we blow it up, and I set that to 2 kilohertz, and sure enough, what we have here is a blip at 2 kilohertz. Now I can show you that by taking the A cursor and coming back here, and you know, if I get right on there and then I could blow it up, you say it looks like I'm right on, and sure enough, here's X sub A up here at 2 kilohertz, 2K, no hertz there. So what happens again is we, with this display, show what frequencies are there. Now with a single sine wave, you don't expect anything other than a single sine wave. But it turns out that this is a great tool to show us what the frequency content of signals are. So I'm going to stop this guy and I'm going to bring it back to 1 kilohertz. Generator. And I probably should have mentioned that before. All the time, you know, if something doesn't look good, very often all you got to do is go back and hit that counterclockwise arrow on the display, and it might take and clear things up. So now I go, and here I've got this guy. Of course, that's the oscilloscope. I don't seem to have anything here, but what's happened is, let me make this smaller. What's happened is I haven't. Oh, interesting enough. What did I just tell you? Let's go back here. Notice that my display starts at 1.75 kilohertz. So here we go. So here's the guy we're looking for, the 1 kilohertz signal. It was an amplitude of 1 before, it's an amplitude of 1 now. And again, if I move the A cursor over there and get right on top of it, if I can, it'll tell me it's, you know, I blow it up a little bit, it'll tell me it's 1 kilohertz. Come on. So I go over here, and it may not be 1, it's 99.7 hertz, close to 1 kilohertz. Now, what I wanted to do is show you the utility of this tool. So let me take and make it a little bit smaller. I'm going to stop this, go over here. And what I'm going to do is take and change this guy to a square wave. So I hit wave. I want to pulse wave, I guess. And let's see what happens here. My period is 1 microsecond. I take the reciprocal, that'll get a 1 megahertz signal. I don't want that. So I'm going to take and make this 1 millisecond. The pulse width then would become 500 microseconds, square wave, and a rise time of 1 nanosecond, fall time 1 nanosecond. That's fine. I hit OK. And now when I run this, I go and make this bigger here. You saw the signal generator. Go and click here, and lo and behold, now I have the 1 kilohertz signal still here, over here on the left, and I've got another one over here, another one here, another one here. Well, what do we have? That's 1 kilohertz. This is 3 kilohertz. That's the third harmonic. This is 5 kilohertz, the fifth harmonic. This one is 7 kilohertz, the seventh harmonic. This guy over here is 9 kilohertz, the ninth harmonic. So it turns out, you might recall that well, when we get to Fourier analysis, it turns out that Fourier analysis shows us that a square wave consists of, and there's one other component, by the way, over here is a DC voltage at 0 hertz. So a square wave consists of a fundamental frequency and the odd harmonics. The amplitude of the harmonics is by their harmonic. That is, the third harmonic is 1/3 the amplitude of the fundamental. If we take a look with C and D here, if I go to C, I get about 3.18 volts. And if I go to the third harmonic, I get somewhere about 1.08 volts, about 1/3. If I went to the fifth harmonic, let's go over here. If I go to the fifth harmonic, what happens is I see I have a value of about 648 millivolts, which is about 1/5 of the 3.2 volts for the fundamental. So this device shows us, this tool rather, shows us what frequencies are in a square wave. Now, interesting thing is a very straightforward equation for a square wave. Let's see if I stop this and play games with it. Let's take this guy here and let's edit the signal generator, and let's make it so the pulse width is only 250 microseconds. So that would mean it's on for 250 and off for 750. So it's a 25% duty cycle signal. Let's hit OK. Watch what happens. Now, this is a little more advanced, but in electrical engineering, you know, you study a lot of mathematics that allows you to take and figure out what frequencies are there. And this guy will do it for you automatically. So let's run it. And here we see the signal generator, the sine wave, shows us the pulses, the very narrow pulses. And what happens now is I've got something at 1 kilohertz, 2 kilohertz, 3 kilohertz, 5 kilohertz, 6 kilohertz, 7 kilohertz, 9 kilohertz. So because I've changed the duty cycle, and when I would do the math, I would discover I've got the odd harmonics still. They're still there. Here's the 3rd, 5th, 7th, and 9th. But lo and behold, I pick up the 2nd harmonic, the 6th harmonic. I'm guessing the next one would be, what's 3 times, 6 times 2 would be the 12th harmonic over here someplace. And again, to do Fourier analysis, you take the integral of the mathematical equation of the wave and integrate it. And what happens is it'll give you the amplitude of these various frequencies. So how you use this tool is, again, pretty straightforward. Now, one thing you could do, I'm going to get rid of this, and let's get rid of it like that, is what if I take and change the y-axis to decibels, and when I do that, hit OK. Now, what we get is something a little weird here. And what's happened is that, notice the scale over here, 200, 0, minus 200, minus 400. Well, dB is 10 times the log to the base 10. So it turns out the scale here, that's the 20th power of 10, 200. That's the minus 20th power of 10. Well, that scale is not very good. So I go to manual, and what happens is I take and I have to, well, let's see which way to go. We'll go this way. Okay, this is a little bit better. Now, if I go this way, what I get is C there is what, 7.133 dB. And if I grab D, well, let's go to the 3rd harmonic. The 3rd harmonic, I get minus 2.467 dB. So I can actually take and have the Y scale in decibels, but you got to play with it to get something readable at times. Sometimes it works pretty well. Other times you take and you got a whole screen full of stuff, and it's because the scale over here has become out of whack. So it turns out that most of the time you want a scale that's, you know, and this is plus 15 to minus 15 or a 30 dB range. If I hit automatic again, notice this is 200 to minus 1000 dB, a 1200 dB range is way too much. And it shows all the frequencies with no differentiation really in their amplitude. Okay, so that's what we're going to do for this little talk.